أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم. In today's lecture we are going to discuss the internal energy of a real gas, and furthermore we also need to discuss the properties of the ideal gas. This topic has been taken from the course outline of thermodynamics, having the course code of PHY331. In this lecture we will try to understand the internal energy of a real gas, and furthermore we need to know the concept of ideal gas and the properties of an ideal gas. At the end we will discuss the similarities between the ideal gas and the real gas and the equation used for the ideal gas and for real gas. First we need to know what is the internal energy of a real gas. For this purpose we need to consider a thermally insulated vessel with rigid walls that is divided into two compartments by partitions. So one compartment is filled with a gas while the other compartment carry vacuum. So what we do, we perform adiabatic free expansion as a result of removing the partition in between the two compartments. So what happen, it is like a free expansion process, but keep in mind as the outside walls of the whole combined two compartments are adiabatic, so no heat will go out of the system or no heat will enter the systems, but only there will be free expansion within these particular systems. So in this case, as a result of this adiabatic free expansion, by removing the partition in between the two compartments, no work is done and no heat is transferred. So the things become complicated whether there is decrease in temperature or not, is the heat and work are equal to zero, so internal energy remain unchanged in free expansion, because if we apply the first law of thermodynamics, then del Q is equal to del U plus del W. So if we consider that the heat enters or leaves the system is equal to zero, and similarly the work done is also equal to zero, so what will be the case of internal energy? Definitely it will be zero according to the first law of thermodynamics. But the things become complicated to understand, that whether the temperature drop occurs in the free expansion or not, so we or whether some changes occur in the internal energy of the systems during the free expansion or not, so we need to know it. So the most important question for us is that whether the temperature of the gas changes, and if changes, how much is the magnitude of that particular change. I means if whether the temperature of a gas during free expansion changes or not, and if it changes, what is the magnitude of this particular change. So there are different experiments performed by different scientists. One of the scientists who tried to understand this mechanism was Joule, and this process is called as the process. His experiment what he performed is called as a Joule expansion process, and he tried to measure the quantity in adiabatic free expansion. He performed this experiment in 1843. So what happened, to measure the change in temperature with respect to constant volume when internal energy is constant, with respect to volume when internal energy is constant, he performed an experiment by two vessels that are connected by short tube and stopcock, and the whole system is immersed in water bath. So what happened, one vessel contained a gas, just like in the previous example, one vessel contained a gas at high pressure while other is evacuated. So the temperature of water is measured before and after the free expansion, as the heat capacity of vessel and water is approximately 1000 times as the heat capacity of air, so Joule was unable to detect the temperature change in the water. So when the when the free expansion process occur, Joule was unable to find the temperature change in water. One of the reason for this is that the heat capacity of the vessel and water is 1000 times greater than the heat capacity of air. So actually they all must they must undergo a temperature decrease of there should be some temperature decrease of by several degree. Instead of measuring the temperature change, that is actually the in free expansion process, for which internal energy of the system remains, consider measuring the internal energy for constant temperature. In this Joule expansion process or in Joule experiment, Joule was finally unable to measure the temperature change due to the free expansion process. One of the possible reasons for this purpose is that the heat capacity of water and the vessel is 1000 times greater than the heat capacity of air. So maybe some of the change occur, but that is absorbed by the water or the water or the vessel. So in that case he was unable. So another conclusion was drawn, and according to that conclusion the scientist was trying to find out the change in internal energy of the systems when the free expansion occur. So another experiment was performed. The internal energy of any gas is a function of two coordinates. If you consider the internal energy of any particular gas is a function of two coordinates among PV and T. So the differential of U is a function of T and V will be it could be written as a du is equal to change in U with respect to T when V is equal to constant, and change in U with respect to V when T is equal to constant, when T is equal to constant. So what happen if we consider there are no changes occurred in the temperature? So what will be the consequences? The dT term will be equal to 0, and the change in internal energy will be also equal to 0. So putting these two values in above equation, what we get? We can get change in internal energy with respect to volume when temperature is constant is equal to 0. This is some conclusion from the from the consideration when we use U, that U is a function of T and V. And in this conclusion it is clarified that U does not depend on V. Further conclusion is that if we consider that U is a function of temperature and pressure, so we can write the change in U should be equal to du is equal to change in U with respect to T when P is equal to constant, and change in U with respect to P when T is equal to constant. So what we do, we apply the adiabatic free expansion condition. In that it is assumed that temperature change is equal to 0 and change in internal energy is also equal to 0. So putting the same values in a equation, what we can get, change in internal energy with respect to pressure when temperature is constant is equal to 0. So by this equation actually states that U does not depend on P. So if we clarify it from both the conclusion, it is clear that if no temperature change takes place in the free expansion of gas, then U is independent of V and P, and therefore U is a function of temperature only. Similarly, to determine that U is a function of T, we need to perform experiment where the temperature is constant and measure change in internal energy with respect to volume when temperature is constant, and change in internal energy with respect to pressure when temperature is constant. We need to measure that. For this purpose, two other scientists perform experiment, Rosny and Franzen. So that experiment was performed by considering another setup, and there was a vessel, and this vessel contain air, it's maybe oxygen or maybe air, maybe mixture of oxygen carbon dioxide in different experiments. So it was concluded that internal energy of real gas is a function of both temperature and pressures. So from this experiment they concluded that the internal energy depends upon both pressure and temperature of the systems. Here it is there is a gas enclosed inside inside a vessel, and there is an outlet, means a gas can go out of it, and the whole system is immersed in water. There is a electric heater to measure its temperature change, to increase to find out its change in temperature, and there is a pressure. With the help of valve we can apply pressure. But anyhow, the result of this experiment was that the internal energy depends upon the temperature and pressure of the system. That internal energy of any real gas is a function of temperature and pressure of that particular system. So what were the disadvantages of this particular experiment? That the heat capacity of gas is much smaller than that of calorimeter and water bath. So this is actually some of the drawbacks of this experiment. And the other thing is that to keep the temperature of a gas constant within reasonable limits, the temperature of water must be kept constant to within less than thousand of a degree. So again, the question arises with the heat capacity problems. So if you want to do the power experiment with high accuracy, so there is some condition for it. To keep the temperature, we need to keep the temperature constant, temperature of the car to within less than thousands of a degree. So it is really very complicated, and for us to calculate the temperature of water to so precise values. So this is one of the problem arise from these experiments. So this is some of the conclusion what we drawn, that the that the internal energy of a real gas depends upon both pressure and temperature. So if we use ideal gas, its properties are a bit different, and its property depends upon its internal energy is not the same like a real gas, but it only depends upon the temperature of that particular ideal gas. So we also need to repeat that internal energy of a real gas is a function of temperature and pressure. But for real gas, when pressure approaches zero, then the equation of state is in simple form, that is equal to P is equal to PV and RT. And the property of an ideal gas are somewhat similar as the property of real gas at pressure. If we compare the ideal gas and real gas with each other, so if we take the property of real gas at low pressures, it could be compared with the ideal gas, and it could be compared with that. So ideal gas should satisfy the following equation, that P is equal to PV is equal to nRT. This is also called as ideal gas equation, and in this case change in U with respect to P when temperature is equal to constant is equal to 0. So it means that when change in internal energy with respect to pressure is equal to at constant temperature is equal to 0, it could be written as in other ways as like change in U with respect to V when T is equal to constant is equal to change in U with respect to P when T is equal to constant, that is multiplied by change in P with respect to U with respect to V when T is equal to constant. So the term in this case, change in P with respect to V when T is equal to constant, is equal to minus nRT divided by V square is equal to minus P divided by V. That is not equal to 0, but the change in U with respect to P when T is equal to constant is equal to 0. So for the ideal case, the earlier equation should be modified as a change in U with respect to V at constant temperature is equal to 0. So we have found that change in U with respect to P at constant temperature, and similarly change in U with respect to V when at constant temperatures both are equal to 0. So we can consider that U is a function of T only. So what we concluded from all this calculation, that the internal energy of the ideal gas only depends upon temperature, but for the case of real gas, the internal energy of real gas depends upon both temperature and pressure. So it is reasonable and accurate to use ideal gas equation for real gas. Whether it is possible to do like that, So real gas at temperatures below about twice standard atmospheric pressure may be treated as an ideal gas without introducing an error greater than a 5%. So the question arises whether we can use the real gas as an ideal gas and we can use the ideal gas equation for real gas. So for this purpose, a real gas at pressure below about twice standard atmospheric pressure may be treated as an ideal gas, and we can use the ideal gas equation for that without introducing an error greater than a few percent. So if we consider an infinitesimal quasi-static process of hydrostatic system, so the first law of thermodynamics could be written as a dq is equal to du plus pdv. So what happened? The heat capacity at constant volume is given as a Cv is equal to change in internal energy with respect to temperature when volume is constant. So for ideal gas, what happened? For ideal gas, we have u is a function of t only. So the partial derivative should be equal to the total derivative. The partial derivative of the system should be equal to the total derivative of the system. So Cv is equal to du divided by dt. And then putting this value in above equation, what happen? We will have dq is equal to Cv dt plus pdv. And this equation will be modified as accordingly as we know that PV is equal to nRT. So the above equation could be modified as a pdv plus vdp is equal to nRT. So first we can modify the first law of thermodynamics as a dq is equal to Cv plus nR into dt minus vdp. And when we divide both sides by dt, so dq divided by dt is equal to Cv plus nR minus vdp divided by dt. So at constant pressure, the left side equation will be equal to Cp, that is equal to the heat capacity at constant pressure, and it is equal to Cp is equal to dq divided by dt at constant pressure, and dp is equal to 0. Then what happened? Then Cp is equal to Cv plus nR. So this is the equation what we get from above equation by putting Cp is equal to dq divided by dt into p values. So the heat capacity of ideal gas at any pressure, and so the heat capacity of an ideal gas at constant pressure is always greater than the heat capacity at constant volume. If we look toward this equation, then it is clarified that the heat capacity of ideal gas is at constant pressure is greater than the heat capacity at constant volume. So it has been concluded from all this discussion that the heat capacity at constant pressure is greater than the heat capacity at constant volume, and the difference between them is equal to that Cp is equal to Cv plus nR. So we can modify. So a question arises why the Cp is greater than Cv. So the answer for this question is that when heat is supplied to a system at constant pressure, then gas expands and work against the external pressure, which is equal to the pressure of a gas in quasi-static process. So that is why the Cp include the work of expansion, which is not found in constant volume heat capacity. So for ideal gas, we can have U as that is equal to internal energy, that is a function of temperature only. So what happen? That Cv is equal to du divided by dt, a function of t only, and similarly Cp is equal to Cv plus nR, that is a function of t only. So we can write this equation as a dq is equal to Cv plus nR into t dt minus vdp. Dq is equal to Cp dt minus vdp. So this is some conclusion what we got, and we have modified the first equation law in respect of that Cp and Cv. So putting the value of Cp it will be like dq is equal to cp dt minus vdp, and writing the same first equation in the form of cv, it will be like dq is equal to cv plus nr into dt minus vdp. So this is some discussion about the ideal gas, the properties of the real gas and the property of the ideal gas, and some similarity between the ideal gas and the real gas. So I hope in next class we will move toward the next topic relating the ideal gas properties. Thank you very much for now.